Hello gems! Welcome to another video of ACE series. The topic that we are going to discuss today is elasticity or mechanical properties of matter, something that does not fit in the thumbnail. Anyways, if you're new to this channel, go check out the description box, know more about ACE series, and I have nothing much to say. Without any promotions, let's begin. So the first question for the day, question 1 over here, Young's modulus of a rigid body is, okay. So it was asked in BITSAT 2012, you can give it a try. You should be ready with your answer in 3, 2, 1. The correct answer is C, infinity, okay. Young's modulus of a rigid body is infinity. How do we know that? Because first of all, Young's modulus is stress by strain, right? By rigid body, they mean a body which will never go under deformation. Whatever force you apply on it, that body is rigid, it will never deform. Okay, so basically there is no change in the dimensions of that rigid body. That is a rigid body, it is not going to deform, it is not going to change its dimension. Okay, so how is strain defined? Strain is change in dimension to original dimension, right? Change in dimension to original dimension. So for rigid body, there is no change in dimension, right? There is no deformation, no change in dimension, strain is 0, right? Strain is 0 because there is no change in dimension. Okay, so strain is 0 means Young's modulus will be infinity. Okay, quite a simple one from BITSAT 2012. As the video proceeds, the difficulty level will increase. Don't worry. Let's move to the next question now. Question 2, it was asked in BITSAT 2011. I think the story is quite evident from the question. In this question, you have a rod of length 2 meters. The bottom end of this rod is attached to a mass of 250 kgs, due to which there will be an extension, right? Extension in the length. It is also given the extension in the length is 0.5 millimeters. Okay, the extension is 0.5 millimeters. Area of cross section is also given, which is 50 millimeters square. You are supposed to find the Young's modulus. Quite a simple, straightforward question, right? If you know the formula. What is the formula? Y is FL by A delta L. Remember this, make this a song. Okay, FL by A delta L, FL by A delta L. Okay, how did we get this? Because Young's modulus is stress by strain. Okay, stress by strain, so force by area by strain, change in dimension to original dimension, change in dimension to original dimension. So we just brought that L to the numerator. Okay, FL by A delta L. So let's substitute the values, we'll get our answer. F is nothing but mg. So mg is 250. We'll take the value of g to be 10, although it's not mentioned anywhere. Anyways, we'll get the approx answer. You can see the only differences over here is in the powers of 10. Okay, we'll get some approx answer. Fl by f, this is f, L is 2 meters, right? Fl by A is 50 millimeter square, 50 millimeters, convert it to meters, right? Convert it to meters, and that is squared. Okay, and delta L 0.5, again convert it to meters. You can see that 250 into 2 will be 500 into 10. I'll multiply this 10 with this, okay, 0.5. So this 10 goes with 0.5, it makes it 5. So 5 into 5, 10 to the power minus 6, 10 to the power minus 3, which becomes 10 to the power minus 9. Okay, one of the 5 cancels with this, 100. Okay, 5 2s are 10, 200 by 10 to the power minus 9, that will get it on top. It becomes 10 to the power 9, okay, plus 9. Now you can see that we have to bring the answer close to 19.6, right? Let's make it 20 because we took approximation over here, right? We took the value of g to be 10 instead of 9.8. So we are slightly getting a bigger value. So make this 20.0. So I just shifted one decimal to the left hand side. So add 1, right? 9 plus 1, 10. So 20 into 10 to the power 10, or it will be 19.6 into 10 to the power 10. Okay, we just made an approximation over there, so we are getting an approximate value. Okay, anyways, option C for cakewalk is the correct answer. Question 3 over here, it's from BITSAT 2013. Let's just read it. side of a cube decreases by 2%, you are supposed to report the value of bulk strain. Okay, so this question actually is just trying to confuse you with the language. Okay, bulk strain, if you see, is nothing but delta V by V, change in volume to original volume. Strain is basically a ratio of change in dimension to original dimension. Bulk strain will be specifically change in volume to original volume. Okay, now volume of a cube will be given by side cube, right? A cube or the side cube. If you see, now the question just becomes a question from percentage error. More than the question from elasticity, it's a question from percentage error now, okay, or relative error. Okay, so delta V by V will be, the power comes down 3 times delta A by A. Okay, I hope you are familiar with the notions of errors and measurement, right? So 3 into delta A by A will be this thing, 2%, which is, you can write it as 0.02. So 3 into 0.02, right? 2% is 2 by 100. Okay, so 3 into 0.02, that will be 0.06. Okay, so the correct answer is option D. D for donut is the correct answer. Okay, so let's move to the next question now. Question 4 from BITSAT 2009. In this question, you are given that the maximum strain a wire can handle is 0.2%, which can be also written in this way. Okay, 2 into 10 to the power minus 3. Young's modulus of that material is given. Load, this much amount of load is applied on that wire. So you are supposed to find the area for which this wire will be able to support this much amount of load. Okay, you are supposed to find area for which this wire will be able to support this much 10 to the power 4 newtons amount of load. Okay, again a simple question, because we are going to use Young's modulus is stress by strain, or you can sing the same song again, FL by A delta L, right? So stress is force by area, strain, since now we don't have delta L and L given, strain is directly given, right? So I'll just substitute a letter for it, E. Okay, strain is E. Y over here on the left hand side. Now since we want to find area, let's get it to the left hand side. What will we get? F by Y into E. Okay, so let's substitute the values and get our answer. F is this load 10 to the power 4, Y is 7 into 10 to the power 9, E is 2 into 10 to the power minus 3. Okay, so let's simplify this. What I'll do is I'll split this 10 into 10 to the power 3 divided by 7 into 2 into 10 to the power 9 minus 3, 6, 2 5s are 10, 5 by 7 into 10 to the power minus 3. Okay, so if you see, this will be less than 1, right? So one more decimal shifting will take place and the answer would be 10 to the power minus 4. Okay, you don't believe me? Let's do it. 5 by 7, okay, 7 7s are 49, 7 1s are 7. Okay, if you see, it will be 0.71 into 10 to the power minus 3, right? So again shift one decimal and you get your option C. C for nothing. Let's go to the next question now. Question 5 over here. In this question, you are supposed to find the maximum load that a wire can handle without crossing its elastic limit. The elastic limit of the wire is given. You are also given the diameter of the wire. Okay, this question is again trying to confuse you with its language, because some of them refer to elastic limit as a point, right? The point at which a material loses its elastic properties, right? So, but the definition of elastic limit here seems quite different, right? It is not just a point, it is giving you a value. Okay, so the second definition of elastic limit is used. Okay, so this is also mentioned in your NCERT. Okay, read it properly. Those who know stress strain curve properly will be able to solve this. Here elastic limit means the stress at the point where elastic limits ends. Okay, where elasticity ends. Okay, so this value is nothing but it corresponds to the stress at which the elastic property of the material ends. Okay, so it is stress. You can also see its units, newtons per meter meter square, right? Force by area. So it is nothing but stress. Okay, so you are given the stress, you are given the diameter. From diameter you can find area, of course. You are supposed to find the force. Okay, so force will be equal to stress into area, right? Just like stress is force by area, force is stress into area, right? So stress is 3.5 into 10 to the power 10, and area will be pi r square. Okay, pi is 3.14 into r square. R will be, this is the diameter. If you see, it is 0.75 means 3 by 4, 3 by 4. This is the diameter, right? Divided by 2, that will give you the radius, and this squared. Now you are supposed to go ahead and solve this. Only calculation part is remaining. After solving, the answer that you will get is option D, I guess. Okay. So the only catch point over here was elastic limit was now the stress itself, right? Sometimes we define elastic limit as the point where the elasticity, the elastic property of a material ends. But in this question, elastic limit was defined as the stress of the point at which the elastic limit ends. Okay, so that was the takeaway point from here, from this question from 2005. Okay, over to the next question. Question 6 from 2014. In this question, you are given 4 wires. Each of them have equal length and they are made up of the same material, which means same Young's modulus, right? So you have to find the thinnest wire among them. The graph of load versus extension for the 4 wires PQRS is given over here. Okay, so how will we go about this? The idea is we are going to use y equals mx. First of all, we are going to sing the same song, which is y equals FL by A delta L. Okay, now we are going to compare this with y equals mx. Okay, so if you see on the y-axis, we have the load, which will be the force. Elongation simply means delta L, the extension. Okay, so let's get this equation in the form of y equals mx. So F equals ya by L, ya by L into delta L. Okay, if you see y equals m will be this thing, so m equals ya by L, and delta L is nothing but x, right? On the y-axis we have f, on the x-axis we have delta L, so this thing will be the slope. If you see y by L, for each of the wire has equal length and they are made of the same material, so y by L is constant for each wire, right? So you can say that m, the slope of each of this line, is directly proportional to the area. Slope of each of this line is directly proportional to area. We have to find the thinnest wire, which means we have to find the wire with the minimum area, the least area, right? So we have to find a line with the minimum slope. So which line has the minimum slope? This, the last line, the option D, right? This one has minimum theta, and tan theta will be minimum for this. The slope will be minimum for this line, OS. Okay, OS, the slope for this line will be minimum, and it will have the thinnest cross section. Okay, so that will be our thinnest wire. You can also watch it another way. Okay, what I'll do is I'll just mark a particular force. Okay, I'll choose a particular force. Suppose this is some F. Okay, I'll fix it. Okay, so I have fixed that F. So each of these points I'm marking now. Okay, for those four wires. Okay, so if you see, the elongation of the P wire is only this much, elongation of the Q wire is little bit more, elongation of the R wire is even more, and elongation of the S wire is the most, right? Okay, so what I did was I fixed the force. Okay, I fixed the force for all of these four wires. Okay, I fixed the force. Young's modulus is same for all of the four wires. Also the length is same, right? So I can bring it in a better format now. A delta L will be FL by Y. Okay, if you see, all three of this are constant. L by Y is already constant because equal length, same material. Now I have fixed F also, and if you see, A will be inversely proportional to delta L, right? So if you want the thinnest area means the maximum elongation, right? Thinnest area means maximum elongation, inversely proportional. So maximum elongation, if you see, is in the case of S, right? So option D again is the correct choice. Over to the next question. Question 7 over here from 2015. In this question, you are given that y is the Young's modulus, x is the strain. You are supposed to find potential energy per unit volume, right? Quite a simple question, directly formula based, okay? Because potential energy per unit volume, you remember the derivation of potential energy stored in a stretch string, right? So that will be given by half potential energy per unit volume is half stress into strain. Okay, so here in this question nowhere stress is mentioned, so we are going to use the formula of Young's modulus, which is stress by strain. So we are going to substitute stress as Young's modulus into strain. Okay, so Young's modulus into strain. So half into stress, in place of stress you have Young's modulus into strain. Strain is x, right? Strain is x, and here also strain x. So the answer that you get is yx square. This is multiply, okay? This is multiply by 2, yx square by 2, okay? Option D. Why is it every time C and D only, okay? So that was a question from 2015, quite a easy one, formula based, right? Let's move to the next question. Question 9 over here. In this question you have two wires, each of them are made up of the same material, they have the same volume. Wire A has a cross section of A, wire B has a cross section of 3A, okay? So if F force is applied on wire A, the extension produced is delta X. You are supposed to find F dash which is applied on wire B, which produces the same extension delta X, okay? I repeat, if F force is applied on wire A, it produces an extension delta X. You are supposed to find F dash which is applied on wire B, so that it produces the same extension delta X, okay? Might seem complicated, but it is quite easy. All you need to do is just equate their Young's modulus, okay? YA equals YB, since they are made up of the same material, okay? So FL by A delta L, okay? So A everywhere. Again here FB by FB, FL by A delta L, and then B everywhere, okay? If you see both of them produce the same extension, right? Delta X, delta X. So delta LA, delta LB equals delta X. So we can cancel them out. Now for F dash, for finding F dash, first we can find the ratio. So FA is nothing but FA is nothing but force on wire A is F, force on wire B is F dash, okay? I brought it over to this side. Let's simplify it now. It will be LB by LA, LB by LA, LB by LA into AA by AB, AA by AB, AA by AB. If you see area of A is A, wire A is A, area of wire B is 3A, okay? So what you get is 1 by 3 LB by LA. Now how to find LB by LA? Now we'll exploit this idea, okay, that both of them have the same volume. So we can say area of A into length of A equals area of B into length of B, because this corresponds to volume, right? Area into length will be volume, area into length will be volume. So both of them have same volume, we have equated them, okay? So you can find we want LB by LA, right? So LB by LA would be nothing but AA by AB. So AA is A, and AA by AB, so A by 3A. So again it will be 1/3. So here what will you get? 1/3 into 1/3, that will be 1/9. So F by F dash is 1 by 9, or F dash is 9 times of f. So f dash is 9 times of f. B is the correct choice. Okay. So I hope the idea is clear. Let's move to the next question now. Question 10 from 2006, you can see that it is almost similar to the previous question. You are given the ratio of radius of two wires. You are also given the ratio of their lengths. You are supposed to find the ratio of their forces for which they have the same extension. Okay, it is given that the two wires are made up of the same material. So what are you going to do? YA equals YB. Young's modulus of A equals Young's modulus of B, FL by A delta L, A, okay, FL by A delta L, B. If you see for same extension means delta LA will be equal to delta LB, these terms will cancel out. Now you have to find FA by FB, FA by FB, that will be A by AB, A by AB, A by AB into LB by LB by LA. So LB by LA. Okay, if you see LB by LA will be 4 by 1, right, or 1 by 4, sorry, LB by LA will be 1 by 4. Okay, and what about AA by AB? If you see AA will be nothing but pi RA square, and AB will be pi RB square. Okay, so if you take the ratio, it will be RA by RB the whole square. Okay, RA by RB the whole square. RA by RB is 2, 2 square 4. So this 4 and this 4 will get cancelled, and the ratio that we want is 1:1. Option D is the correct choice. Okay, I hope this is clear. Okay, just like the previous one, similar approach, right? So let's move to the next question now. Question 11 over here from BITSAT 2006. Now I think I messed up with the question numbers, but don't mind that. Let's focus on the question. The question says that we have a rod of density rho. The length of that rod is L. Y is the Young's modulus of the material of that rod. Delta L is the extension in its length due to its own weight. You can see mg in the downward direction, right, or mg towards the center of the earth, due to this force, due to its own weight, there is an extension in the string which is delta L. You are supposed to find this delta L. Okay, so again the same song, y equals FL by A delta L. Right, now let's find delta L. Delta L will be F L by Y A. Now since it's a linear relation between delta L and L, since delta L is proportional to L, or delta L is proportional to L to the power 1, we can use the concept of center of mass. We can treat that this mass is entirely located at the center, okay, at an distance of L by 2. If you see, the mass is uniformly distributed over a distance L, right? The mass is distributed over its entire length, but we can assume, since it's a linear relation between the two, we can assume that the entire mass of the rod is located at its center, which is at L by 2. Okay, so let's substitute the values over here. Here force will be mg, the weight, right? We'll put it as weight into, or mg, let's write mg into L. L in our case now it will be L by 2, right? In our case it is L by 2. Entire mass is located at a distance L by 2. Okay, y Young's modulus y, and area, okay, we'll keep it as A. Now you can see that mass of this wire is not given. In place of that we are provided with density, right? So we can use mass is equal to density into volume. Okay, density into volume. In place of mass I am substituting density into volume, GL by 2 by Y into A. Again I can write this volume as area into length, right? Area into length. Okay, so what will I get? You can see that this A and this A will get cancelled, and 2 also I have in the denominator. So what I will get is rho g L square by 2y. Rho g L square by 2y. Rho g L square by 2y. Option B is the correct choice. Okay, you can also proceed by the safest method, which is integration. Okay, you can cut a piece dx and then integrate and you will reach the same answer. Okay, since it was a linear relation between the two, I chose the concept of center of mass. Center of mass cannot be applied if the relation was not linear. You remember we used to apply center of mass even to problems regarding our potential energies, the chain drag problem, pull the chain back to the tabletop, right? Because potential energy is a linear relation, right? It has a linear relation with h. You can see that it is dependent on the first power of h, okay, directly proportional to h. In case of potential energy, and here also it works, right? Because there is a linear relationship between the two. Okay, anyways, over to the next question. You can also try it by integration as well. Okay, you will reach the same answer. Anyways, over to the next question. Question 12 over here. In this question, we have a string of length L. In case 1, we apply a load of T1. The length of the string becomes L1. In case 2, we apply a load of T2. The length becomes L2. Okay, you are supposed to find this original length in terms of this L1, L2, T1, T2. Okay, using that data. Actually, it's quite simple. You can see that we began with the same string. In this both cases, case 1 and case 2, the string is the same, right? String is the same, made up of the same material. Young's modulus will be the same. Okay, Young's modulus in first case equals Young's modulus in the second case. Basically the same string, right? The only thing if that we are changing is this T1 and T2, the load. Okay, so Young's modulus, as we know, it is FL by A delta L, right? So in case 1, it is T1 into L. This is the original length. Okay, how is it the original length and not L1? See, this L comes from strain, right? If you see, the formula comes as Young's modulus is stress by strain. Stress, force by area, and strain is change in dimension to original dimension, change in length to original length. So this L is the original length, which is small, this L. Okay, original length with which we began. Okay, this length. Now area, let's write it as A. Okay, area will be A, and delta L. What will be delta L? Let me write this properly first. Okay, what will be delta L in case 1? You can see that the initial length was L. Okay, then the length changed to L1. Okay, so delta L in the case 1 will be L1 minus L. You can say that delta L in this case will be final minus initial. Final minus initial. So that is L1 minus L. Okay, and in that case it will be again T2 into L, the original length, right, upon A. Okay, A area is the same. Okay, and L2 minus, in this case it will be L2 minus L, final minus initial. So L2 minus L, L gets cancelled, A gets cancelled, T L2 minus, I'm just cross multiplying, T1 L2, T1 L1, T1, sorry, it's L over here, so T1 into L equals T2 into L1 minus T2 into L. Okay, so what I will do is I'll bring this L terms together since I want to find that original length. So T1 L and this T2L, I'll bring it to the left hand side, T2L, so that becomes positive. T2L1 remains on the right hand side, and I'll push this to the other side, making it minus T1L2. Okay, so from here I'll take L common. So L is common. So you can see T2 minus T1 over there, T2 minus T1 equal to T2 L1 minus T1 L2. Okay, so L is nothing but T2 L1 minus T1 L2 upon T2 minus T1, T2 L1 minus L2 T1 upon T2 minus T1. Option C is the correct choice. Okay, so that was a bit tricky. You can rewind the video and watch it again. Let's move to the next question if you have understood it. So question 13 over here, in this question we initially had a string of length 2L. To that we attached a mass M at its midpoint L. Okay, so the string came down. Okay, the string came down a distance x. X is very much less than L. It's a small distance, but you can see the string over here now, AOOB. Okay, initially it was at AB. Okay, you are supposed to find the strain in this case. Okay, I was actually supposed to leave this question for homework. Now I realize that this question is a bit tricky, a bit difficult, and it's the most recent question that we are discussing today. Okay, and moreover I need watch time, so let's just do it. Okay, so strain will be given by change in length to original length, right? Here we cannot use our Young's modulus logic and all. We have to go by pure logic. Okay, so strain will be change in length to original length. If you see the original length, let me write it this way, small l, not to confuse with that L. Okay, so if you see original length was nothing but initial length, which is 2L. Initially the string was over here, right? So original length was 2L. Now the length has changed. Okay, so now we have to find the change. Okay, just find the change now. Change will be, if you see, the change will be final minus initial. Finally, if you see, the string is at AOB. This is the string. Okay, so final length will be AO plus OB. AO plus OB. Final length AO plus OB. Initial length was AB. Okay, which is 2L. So if you can find the values of AO and OB, that will be easier, right? So let's find it from this triangle. Okay, I'm just isolating this triangle of length L over here and this height x. Okay, base L, height x. Okay, now this being the hypotenuse will have the value under root L square plus x square. This will have value under root L square plus x square. In similar fashion over here, this hypotenuse will have the same value, right? Symmetric situation you can see over here. So AO equals OB equals this thing, right? So that will give us 2 into under root L square plus x square. Okay, minus AB is 2L. So 2, I'll take L square common from here, L square, and I'll write it in this way, x 1 plus x square by L square. Okay, minus 2L. You'll come to know why am I doing this, because I can take 2L common from here. This L square will come out of the root sign and you'll be left with under root 1 plus x square, x by L the whole square, right, minus 2L. So I can take that 2L common and I'll be left with 1 plus x square by L square whole raised to half. Okay, I'm converting that root sign to raised to half. You can write it that way also. Minus 1. Okay, I took that 2L common. Here, since x is very much less than L, we can bring this half down. Okay, this is according to the binomial theorem. Okay, so we are using that logic. I hope you know about it. So yeah, so since this x is very much less than L, we can bring that power down. So let's do that. Okay, if you didn't know, please note it down now. So that will give us 2L into 1 plus half x square by L square, right, and minus 1. Okay, so I just brought that half down. Okay, now you can see that this and this will get cancelled, and what we'll get also this 2 and 2 will get cancelled. L will get cancelled with this x square by L and x square by L. Okay, unfortunately this is not the correct answer because this was change. Remember that we want strain. Strain is if you see, strain is, now I also got lost. See, strain is change in length, this change in length divided by original length 2L. So that will be x square by 2L square. If you see, this is dimensionally incorrect, right? X square by L has some dimension. Strain does not have any dimension. C is not the correct option. Even this one won't be the correct one. A is the correct choice. Okay, so this was the change. This was the change. Change divided by the original length will give us the strain. Okay, so that was our answer. I hope you are able to grasp this one. You can rewind the video and watch it again. I know it's a tough one. Okay, so yeah, that was a tough one. So that's why I did it, right? Okay, you can note it down as well if you wish to. Okay, so that's all for today's class. I hope you enjoyed it. I'll see you soon in the next class. Stay home, stay safe. # no promotions for today. Keep enjoying physics.